So VSEPR theory, or VSEPR, or VSEPR theory, depending on how you want to pronounce it, is a theory that's used to predict and explain the shapes of molecules and polyatomic ions around one central atom at a time, or to predict the orientations of atoms within larger structures like diamond and graphite. It's also used to predict and explain angles between bonds in molecules and polyatomic ions. So why is this necessary? Well, knowing the geometry of little molecules and structures within larger structures is going to be super important for understanding whether or not something is polar, whether or not its charge is spread around evenly or not, which leads directly into the concepts of intermolecular forces, the attractions between molecules, which affect things like boiling point, melting point, volatility, and solubility. And it can also have some context in sort of like biochemistry, stereospecific reactions and such like that, which is mainly an HL topic. But just to mention it, that the geometry and the orientation of atoms within molecules can have major impacts on the properties, both physical and chemical, for that molecule. So what does it stand for? Well, it stands for Valence Shell Electron Pair Repulsion Theory, VSEPR. The short explanation is that in the valence shell, electron pairs will repel each other as far as possible. So that's where the letters come from. The longer explanation is, if you think about atoms bonding covalently, they're sharing electron pairs. But there's also going to be electron pairs that aren't involved in covalent bonding, and those are called non-bonding electron pairs or lone pairs. And so even though the covalent bonding is highly directional, which means that the pair of electrons are stuck between those two nuclei, and they have to stay between those two nuclei and only those two nuclei. When you have multiple electron pairs around an atom, the exact way that they orient relative to each other can change. That's not set in stone. So the theory is that since all electron pairs are negatively charged, they repel each other as far apart as possible while still remaining around the central atom. And so the orientations of the atoms in a molecule or a larger covalent structure and the exact angle between them can therefore be predicted if you know the number of what we're going to call electron domains, and if you know a little bit about some simple geometry. So an electron domain is just a term for a region around an atom where there is negative charge. Things that count as electron domains are single bonds, double bonds, triple bonds, and non-bonding electron pairs. All of these count as one electron domain. So when we consider shapes and things, there are two different kinds of geometries that we're going to consider. One is called the electron domain geometry, which is a bit simpler. And then one is the molecular geometry, where we ignore where lone pairs are and we only describe the shapes of the atoms within a molecule or a polyatomic ion. Okay, so here are the basics. If you have something that has two electron domains, so something that has two places where there's negative charge, usually for two, it's two places where there are covalent bonds. Those two covalent bonds, or those two pairs of electrons, are going to repel each other as far as possible around this central atom. And so if those two things are stuck to this central atom, the farthest that they can get away from each other is being directly on opposite sides of one another. And so when you have two electron domains, they always end up taking this shape, which is known as a linear orientation. And those things get 180 degrees away from each other. When you have three places that have negative charge, they're all still tied to this central atom because they have to stay between these bonded atoms. So the farthest away they can get from each other while still remaining around the central atom is 120 degrees. And so this shape here, it looks very triangular. It's also flat, and therefore it's called trigonal planar. So three electron domains gives this orientation, trigonal planar. The last one is the only one for the SL content that goes into 3 dimensions. So it's not flat. It's called tetrahedral. This tetra word comes from the Greek for 4, and it refers to that if you made a shape out of this, it would be a four-sided shape. So when four things repel each other, all tied to a central atom, they get 109.5 degrees away from each other, and they sort of form like a tripod. You can think of this in 3 dimensions. It's like a tripod with one sticking straight up. And so all 4 of those are exactly the same distance apart from one another. So we've mentioned some things about bond angles. So it's the angle between, if you think of these 3 atoms here that are bonded together as being the 3 points of the angle, the bond angle is the angle between those 3 atoms and their bonds. And so we'll look at that in a subsequent video. Okay, so those were just the electron domain geometries. Their names are linear, trigonal, planar, and tetrahedral. There's only 3 of them to know, and they are for when you have 2 electron domains, 3 electron domains, and 4 electron domains. Molecular geometries are a little bit different. There are more than 3. In fact, for SL, there's going to be 6. Because when you have non-bonding pairs of electrons as one of your domains, you then won't have one of these names as your geometry. So it's helpful if we use an example. So here's BF3, here's SO2. Here are their Lewis structures. And if I count the domains, there is 1, 2, 3 single bonds around boron, so there are 3 electron domains. Around SO2, there is a single bond, a double bond, and a non-bonding pair of electrons, all of which count as 1. There's also 3 electron domains around sulfur. So for both of them, they're going to end up taking this orientation of with their electron domains of trigonal planar. Both the S and the B have a trigonal planar electron domain geometry. So if you got that question and you were asked what their electron domain geometry was, the answer would be the same for both. The answer would be trigonal planar because of the three regions of negative charge. But their molecular geometries are not the same, because for this one, if you fill in the atoms, there's an atom at the end of every single bond in boron. Every single electron domain has an atom at the end. So for this one, the molecular geometry will also be called trigonal planar, because that describes how the atoms are oriented as well. If we fill in the atoms and the lone pairs around sulfur, though, if I put an oxygen here and I make this the double bond to oxygen, this third domain, though, is a lone pair. And so when I actually name the shape of the molecule, I do not include that in describing the shape. So now I'm trying to describe what that shape is, and that is now no longer a trigonal plane. It only has sort of these 3 atoms in it, and this is actually called bent or V-shape. So while the electron domain geometry would be called trigonal planar in both, the molecular geometries are different. This one is called trigonal planar, and this one is a new shape that's called bent or V-shaped, because when you only look at the atoms, they have this sort of bent arrangement to them. So when deciding on a molecular geometry, the positioning of the lone electron pairs is still influential, but where they are is ignored, and only the shape of the atoms are described. And so in the end, what we're going to see is that there's only one shape that you can really get out of 2 electron domains. It's always linear. When you have 3 electron domains, there are 2 molecular geometries. There's the original trigonal planar, and then there's one that looks like this, where it's called bent. And with 4 electron domains, there's going to be 3 possible shapes. There's the one like this, where it's tetrahedral. There's going to be one where 3 of them involve bonded atoms, and then there's 1 lone pair, and we call that trigonal pyramidal. And then there's going to be one where only 2 of them involve atoms bonded at the end, and 2 of them are lone pairs. And this one is also going to be called bent. So we've got this one being called bent, this one being called bent or V-shaped, and this one, I did a little zoom there. Sorry about that, in slow motion. And this one is called trigonal pyramidal. Trigonal pyramidal. So bent, trigonal pyramidal, and bent. The other names are linear, trigonal planar, and tetrahedral. So the steps to go through is draw your Lewis structure, count the number of domains. The domains give you the electron domain geometry, which in both of these cases was trigonal planar. And then draw in atoms at the end of those domains and see if the molecular geometry is also trigonal planar, or whatever the original electron domain geometry is, or if some of those are lone pairs, non-bonding pairs, then you're going to have to come up with a different name for that shape. And we'll do plenty of practice on this in class, but those are the basic steps to assign electron domain geometries or molecular geometries.